Welcome to today's presentation on EQ cold-formed steel studs. This is one in a series of educational programs offered by the Steel Framing Industry Association, or SFIA. This presentation is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of this presentation without written permission from SFIA is prohibited. At the conclusion of this presentation, you'll be able to walk away with a basic understanding of the key differences between traditional or standard CFS studs and EQ studs for use in non-structural applications. We'll also review the important standards that govern EQ and standard studs, and look at specific requirements for design and coatings. We'll close out by demonstrating how to use limiting height tables and with a brief discussion on fire and acoustic ratings. Let's start with some background on cold-formed steel. The primary raw materials that comprise steel are iron ore, coke, and recycled steel. Iron ore is a naturally occurring metallic oxide, an oxide that makes up about 5% of the Earth's crust. Coke is coal with a high carbon content. Coke is a naturally occurring material, and the World Steel Association estimates that there are at least 100 years' supply of coke. Perhaps one of the most important ingredients in steel, given today's concerns over sustainability, is recycled steel. The construction industry boasts an 85% recycle rate for steel. The Steel Recycling Institute reports that steel is recycled more than paper, plastic, glass, copper, lead, and aluminum combined. From a sustainability standpoint, the EPA states that the U.S. steel industry has reduced greenhouse gas emissions by 47%. Also, the World Steel Association reported that since 1975, the world steel industry has lowered energy consumption by 50%. Sheet steel that is used for CFS studs and other products is protected by a coating and then shipped from the mill in coils. The industry standard for corrosion resistance is galvanization, which means coating the steel in zinc. The upper picture here shows galvanized coils of steel that are ready to leave the steel mill. There are other coatings that are also used to provide protection against corrosion, although galvanization is the most common process. At the steel stud manufacturer facility, the coils are slit into blank widths. Each product profile has a blank width associated to its shape. The coils of blank width are then fed through a series of dies, shown in the center picture, in a continuous process where the dies gently bend the steel into its final shape. The picture at the bottom depicts some of the more typical profiles that are used in the construction industry. They include studs, tracks, furring channels, Z-channels, and various accessories. The studs are manufactured to be either structural or non-structural in the form of a C-shape. Today, we're going to focus on non-structural studs and specifically EQ studs. CFS shapes used in construction come in a wide range of sizes and thickness. The wide range of depths and thicknesses allows for optimization of design to meet specific design requirements. In the past, we called out the thickness of steel in gauges. Now the industry has moved to mils. A mil is the uncoated material thickness as expressed in 1/1000ths of inches. The strength and stiffness of CFS framing members are based on their profile or shape and their material thickness. The standard stud joist profile is shown here on the right. It's made up of stiffening lips. They can be described as the small returns that come off the flange and in the diagram run vertically. They help stiffen the two horizontal lines that are the flanges. The web is the single long line that is running vertically in the diagram. The industry has adopted standard descriptors to identify the individual members that define the profile and therefore the strength and stiffness of the member. The first descriptor, shown here as 362, is a number that provides the member depth. Member depths are given in hundredths of inches. Therefore, a 3 5/8 inch stud is called out as 362. The second defines the application of the member. There are basically four profiles that make up the cold-formed steel line. They are S, which is stud or joist, T, which is track, U, which is channels, and finally F, which is furring. Some manufacturers also produce L-header members. The flange width is important. It's also given in hundredths of inches, which means that a 2.5 inch flange is designated as 250 as shown in this example. The last number, 54 in this example, is the thickness of the steel. It's given in mils or thousandths of inches. When you put this information together, you get a 362S 250-54 member as the designator. Moving on to an EQ stud, the most basic definition is that an EQ stud is a stud that is similar in shape to a standard C stud, but has some unique features about it that allow for thinner sections while still meeting the same performance as a standard stud. Thus, the EQ or equivalent designation. EQ studs are proprietary to each manufacturer. They were introduced over the past decade or so, but now they're the predominant stud for non-structural uses in the United States. Characteristics of two common EQ studs are shown here. The important points are that the shape is slightly different, materials are thinner, and yield strengths are higher than conventional studs. Just as the structural performance as dictated by these characteristics must be equivalent or greater than a conventional stud, the same performance requirement applies to the corrosion protection or coating. We'll discuss this more a little bit later. How can an EQ stud that is thinner than a conventional stud perform the same or even better? The answer is partly in the steel itself. Higher strength steels make a product stronger, allowing for a reduction in the product's thickness and also a reduction of weight and cost. Additional reinforcing due to changes in the configuration of the stud also strengthen it, such as adding ribs or lengthening lips. The coating is a separate issue that we'll discuss in more detail, but basically there are new coatings applied over zinc that meet the code requirements for CFS members. The development of alternative cold-formed framing or equivalent type products is the result of improved technology, high-yield strength steels, and new design configurations for the products themselves. The introduction of these products into standards such as ASTM C645 also helped facilitate new products. Prior to the introduction of EQ studs in June of 2005, there had not been any substantive change in non-structural drywall studs in over 20 years. Today, a majority of manufacturers throughout the United States are producing EQ stud products as their standard product offering. There are also some market drivers, as shown here, that make EQ studs appealing. These factors have made quite a transformation, with EQ studs now representing over 90% of the non-structural market. This slide illustrates the difference between the non-structural drywall and an equivalent or EQ stud. The higher yield strength of the EQ stud makes up for the thinner material in this case. In recent years, there's been a transition period where the requirements that govern CFS framing have moved from the ASTM standards we've seen for decades to the standards maintained by the American Iron and Steel Institute, or AISI. As of the publication of the 2018 International Building Code, the transition is pretty much complete. As you can see here, designated by the red arrow, AISI S220 is the only standard referenced for non-structural studs in the 2018 IBC. But there are many secondary standards referenced in the AISI 220, so it's still not a completely self-contained standard. Fortunately, SFIA has taken some of the mystery out of code compliance with its Code Compliance Certification program. This is especially helpful for specifiers, designers, and code officials for EQ studs. Before we touch on the SFIA program, a quick definition will help so you know what type of studs we're discussing when we use the term EQ. Actually, this definition applies to any non-structural application. We're basically talking about interior studs that have limited live loads. For example, a partition wall. AISI S220 places limits on what can be called non-structural. As you can see, it's set at 10 psf for a load perpendicular to or out of plane from the wall. Some special locations, such as pressurized plenums, have higher allowable loads. Members are also limited to axial live loads of 100 pounds per foot, or a point load exceeding 200 pounds. Anything above these limits needs to be designated as a structural application. An EQ stud, as defined in the appropriate standards and the SFIA Code Compliance Certification Program, must have a bending moment strength that is at least equal to that of their traditional stud counterpart, have developed and published composite limiting height tables in accordance with ICCES AC86 2010, have published screw data, shear and pullout, and must pass the screw spinout performance test in AISI S220, section A6.6. Meet the applicable corrosion protection requirements. Most of these requirements are also drawn from AISI S220. Note that this program, and thus all code requirements, are mandatory for SFIA members for EQ and conventional framing products. Look for the label to be certain that you're getting a code-compliant product. So what exactly is AISI S220 and what does it cover? We'll go over the main items in it, but let's start with the title. AISI has a series of standards, and this one is called North American Standard for Cold-Formed Steel Non-Structural Members. These are some of the important items covered in the standard. Material requirements for steel, protective coating requirements for members, minimum thickness requirements, minimum physical configuration, manufacturing tolerances, knockout requirements, and marking and identification requirements. The important point here is that AISI S220 references ASTM A1003 standard specification for steel sheet, carbon, metallic, and non-metallic coated for cold-formed framing members for the steel that's used to make a stud. A1003 covers yield strength with a 33 KSI minimum and coatings that are permissible. ASTM A1003 also sets a 75-hour minimum duration for this test. A coating passes the test if it does not lose more than 10% of its coating after 75 hours. The actual testing is conducted according to the test method in ASTM B117. As an alternative material design or method of construction, EQ studs are approved under Section 104.11 of the IBC. EQ studs are typically certified through third-party testing in accordance with ICCES AC86. In fact, many manufacturers of standard studs use limiting height tables developed by testing under AC86 as an alternative design method. Limiting heights tables under AC86 are developed using calculated performance based on test data. Thus, for structural performance, EQ studs meet code but through a different route using testing. But what about the coating requirements? AISI S220 requires a minimum G40 or equivalent corrosion protection. The key with EQ studs is the phrase equivalent corrosion resistance. As we covered a few minutes ago, ASTM 1003 is referenced in AISI S220, and that's where the equivalent requirements reside. The allowance for equivalent corrosion protection or alternatives to galvanized coatings created opportunity for the use of innovative coatings for CFS framing members. These coatings can be applied over an existing zinc-based coating to increase its corrosion resistance so that it meets the salt spray test requirements in ASTM A1003. In some ways, these coatings might be even thought of as an added protection, given that they react with and adhere to the existing coating. Imperfections in the original coating are covered up to make sure the entire surface is protected. Remember from this slide used earlier that an EQ stud still has to meet other requirements. We've already talked about some of these, but we still want to go over a few key additional items, such as moment, limiting heights, and screw data. We'll also discuss knockout and labeling requirements, but just briefly. When it comes to holes manufactured in a stud, both EQ and conventional studs must meet the same requirements. AISI S201 is the product data standard for cold-formed steel framing members. Among other items, it governs holes in webs, also called punch-outs, cutouts, knockouts, perforations, etc., to allow the passage of utility surfaces through the studs. Unless specified otherwise by the manufacturer, factory punch-outs comply with the following conditions. First, punch-outs shall be spaced along the center line of the web of the framing members. Second, punch-outs shall have a center-to-center spacing of not less than 24 inches. Third, punch-outs shall have a width not greater than half the member depth, or 2.5 inches, whichever is less. Fourth, punch-outs shall have a length not exceeding 4.5 inches, and fifth, the distance from the center of the last punch-out to the end of the member shall not be less than 12 inches, unless otherwise specified. Any configuration or combination of holes that fits within the punch-out width and length limitations is permitted. I really can't stress enough the importance of being able to identify properties of studs in the field. Labeling is what installers and code officials rely upon to do their jobs correctly. There are two levels of markings. One is group or skid labeling, and the other is individual member labeling. AISI S220 has a specific section on identification of groups of like members. Groups of like members must be marked with a label or a tag attached thereto. Markings include the roll former's identification, such as name, logo, or initials, length, quantity, the manufacturer's member designators, including member depth, flange size, minimum steel thickness in mils or inches exclusive of the protective coating, and the designation in S for non-structural. AISI S220 also addresses identification of individual framing members. This duplicates the group marking information, but includes a little additional information too. It states that members shall have a legible label, stencil, or embossment at a maximum distance of 96 inches on center on the member with the following information: roll former's identification, minimum steel thickness in mils or inches, exclusive of protective coatings, minimum yield strength in kip per square inch, if other than 33 ksi, protective coating type and weight. This can be omitted if the standard G40 coating is on the studs, the designation in S for non-structural studs, and although not required, EQ may be listed for coatings on some studs. Remember, part of the requirements for an EQ stud is that its allowable bending moment must meet or exceed that of its comparable conventional stud. This chart shows this graphically. Along the same lines, screws for EQ studs must meet performance requirements established by testing. According to AISI S220, When tested in accordance with Section 10, members shall be capable of pulling the head of the screw below the surface of the gypsum board in less than 2 seconds without spin-out. If it fails to do either of these following the test procedure in the standard, then the member fails. EQ products on the market must meet this criteria, and the screw test data must be published under the SFIA program. Just as an example, values shown in the top half of this table are for a proprietary EQ stud product. The values are predominantly based on the steel thickness and yield strength. Since EQ studs are formed from steel with a higher yield strength, they have greater pullout and shear values. The chart illustrates this difference. Higher pullout values are advantageous when attaching handrails, fixtures, etc. The last structural issue we want to address is limiting heights. This is basically a height restriction placed on a wall assembly or studs based on the loading and the stud's mechanical properties. Limiting heights tables basically do the engineering for you in selecting the stud for a given wall. There are multiple sources of limiting heights tables for conventional CFS sections. This is an example from SFIA's technical guide. The tables typically show the maximum allowable height for the application, that is, whether it's composite or non-composite, and the load conditions for the specific type of member. Members must be built as specified in the tables when classified as composite assemblies. For EQ studs, the manufacturer of the product must supply the limiting heights tables for each product they produce. Although this isn't a seminar on stud selection, we will review briefly some limiting heights examples so you understand how it's applied and that there is not much difference in using tables between a conventional and EQ product. A good resource paper on limiting heights for non-structural CFS walls is available from SFIA on their website. The link at the bottom of this slide will take you there. Or just go to cfsteel.org and search for limiting heights in the search box on the home page. Although this is focused on limiting heights issues, it includes a lot of information related to EQ studs, including some we're looking into today. It's a good resource for you. In this example, we have an 11-foot, 10-inch non-composite wall. With non-composite assembly, the capacity of the assembly, and thus its allowable or limiting height, is based only on the stud itself. This is an interior drywall partition. In the chart at the bottom, we extracted stud information from the SFIA technical guide for the first 2 rows and similar data for an EQ stud from a manufacturer. These are not the only studs that could be used, but if you examine the chart, you will see that each meets the load and deflection criteria for the given wall height. All of them exceed the 11-foot, 10-inch wall height. This is a limited stud selection example because you would also need to consider any fire separation ratings or acoustic ratings that may be specified. But the main point here is that the only difference between a conventional stud and an EQ stud is the source for the limiting height data may be different. EQ limiting height data must always come from the manufacturer. Just another quick example, this time of a fully composite wall. In this case, that means the height is based on the contribution of the entire assembly with the gypsum board in place, versus just the capacity of the stud, as in the prior example. But the point is that we were able to find both an EQ solution and conventional solutions from readily available and published sources. Before we conclude, I want to touch briefly on 2 other issues that come up with EQ studs: fire and sound. With fire and sound ratings, the rules are the same for EQ members as they are for traditional or conventional steel framing. For fire-rated partitions, installation of the wall assembly must adhere exactly to the way the assembly was actually tested, or it is not in conformance with the tested assembly. One positive about EQ studs is that today's commonly used fire-rated assemblies using conventional studs were tested decades ago, and there isn't a requirement for periodic retesting, despite the fact that some materials have changed over this period of time. Conversely, fire-rated assemblies using EQ studs have been recently fire tested, and the materials represent what is being supplied today. What we say here about fire-rated assemblies also applies to STC ratings for acoustical requirements. The important point is that the as-built assembly must match the tested assembly or engineering analysis to achieve the listed STC rating. These are a few suggestions for making sure you meet fire and sound criteria. The bottom line is verify. Compare literature and submissions with the plans or partition schedules, and compare field members to the approved assembly requirements. Given that all products are required to be labeled, this is not a difficult task for EQ or other code-compliant studs. Now that we've covered the major objectives set out at the start of today's program, let's summarize some key points. As you can see here, the big takeaway is that traditional and EQ studs must meet the same basic requirements as the conventional studs that you've used for decades. So whether it's coatings, labeling, or loads, you can be sure of what you're getting when you select code-compliant EQ and conventional products, such as those from SFIA manufacturers. There's one final set of key points that I'd like to emphasize. First, EQ studs are not really a new or unusual stud in the market anymore. They are the predominant product being used in the market for non-structural applications. Second, you don't need to worry about performance. Code-compliant EQ studs, just like conventional studs, meet the product requirements and the applicable standards that govern CFS framing. Last, if you want to be sure the standards are being met, the SFIA label is the best place to start. Thank you for viewing this presentation. For more information, visit the SFIA's website at cfsteel.org.